If your app answers the same question 100 times a day, you're lighting tokens on fire. We will build a semantic cache with embeddings, so near-duplicate queries reuse answers instead of recalling the model. You open a support inbox and see the same phrasing over and over. Each time you call the model, you pay latency and cost. After this video, you will have a simple pattern to detect near duplicates, reuse prior answers, and measure saved tokens in Python. No heavy math, no black box, just practical, testable steps. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Think of semantic cache as a short list of prior questions and their answers. When a new question arrives, we check if it is similar to something we already answered. If it is similar enough and safe, we return the old answer and skip the LLM. That reduces cost and speeds responses. People reach for this when they have repetitive queries, FAQ bots, or bulk processing of user text. The basic idea is intuitive. Represent questions in a compact way. Compare a new query to stored queries, rank the matches, and then decide if reuse is safe. Here we start with a tiny toy corpus so you can see every step. We use simple set-based similarity, so the logic is explicit. The weakness is obvious. Bag of words misses deep paraphrase. The strength is clarity and immediate savings for high repetition. We will build a minimal pipeline that seeds a cache, scores a query, ranks matches, applies a safety guard, and then returns a cached answer with a token savings estimate. That is the exact flow most production caches follow, but shown here in a tiny, debuggable form so you can evolve it. Now we will seed the cache and build a tiny vocabulary. This snippet seeds a tiny Q&A cache and extracts a simple vocabulary. We start with QA, a list of short question-answer pairs representing prior model responses. The set comprehension collects unique lowercase words from each question to build vocab, a minimal bag of word space for later similarity checks. Using questions instead of answers keeps the matching focused on user intent rather than response phrasing. Keeping the vocabulary tiny reduces compute and makes edits easy when debugging. The printed count shows the semantic space size we will use for caching decisions. In short, this snippet builds the small memory our later functions will compare against. Next, we will compare a new query to the cached questions. This snippet computes Jaccard similarity between the query and cached questions. The variable query holds an incoming user ask, which we tokenize into a set TQ. For each cached question in the list QA, we form a set S and calculate the intersection over union to get a similarity score. We collect these scores in scores and take the maximum as a quick proxy for the best semantic match. The result sim is rounded for readability. Higher similarity suggests the cache likely has a relevant answer, and the printed value shows how strong the best match is. This gives a cheap, explainable measure of overlap between phrases. Now, we will pull the best candidate matches from the cache. This snippet ranks the cache by similarity and returns the top two matches. We reuse the token set TQ for the current query and build pairs, a list of score and question tuples using Jaccard similarity. The function heapq.nLargest efficiently picks the best candidates without sorting everything, which scales better as QA grows. We extract just the question texts into top for clarity. If you increase K from 2, you'll see more candidates, improving recall, but potentially widening the review set and adding latency. The printed list shows the highest value reuse options in order. This step turns similarity scores into a manageable shortlist for review or automated reuse. Next, we will decide if reusing an answer is safe. This snippet decides whether to reuse an answer using a threshold and a guardrail. We define unsafe as a tiny block list and set guard to false if the query mentions sensitive terms. The value tau is a similarity threshold. We recompute best, the top Jaccard score, across the cache. The final hit condition requires both best to exceed tau and the guard to pass, preventing risky cache reuse. Increasing tau reduces false positives but misses more borderline matches. Decreasing it does the opposite. The printed Boolean tells you if the cache will be used safely. This is the control logic that prevents embarrassing or dangerous auto-replies. Finally, we will fetch the cached answer and report savings. This snippet returns a cached answer when safe and reports tokens saved. We treat rate as a simple token cost per query word. If hit is true, we fetch the top matches answer from QA using the first item in top and compute saved as avoided LLM tokens. Otherwise, we call a mock path and save nothing. This pattern gives a minimal, debuggable cache wrapper that short-circuits repeat work. Raising rate amplifies the reported savings, helpful for estimating dollar impact. The printed number quantifies immediate latency and cost avoided by the cache. Use this wrapper to see direct, measurable wins before you scale. Applied to a real project, this tiny example maps to a larger system by swapping the bag of words for embeddings and the Jaccard test for cosine similarity. You would also replace the tiny block list with a content safety service and the linear scan with an approximate nearest neighbor index. The control flow and checks remain the same. Recap: it is a semantic cache that reuses prior answers by matching new queries to stored questions. Use it when queries repeat commonly and cost or latency matters. Caveat: simple set similarity misses deep paraphrase and needs safety guards. Next step: tune the similarity threshold tau and measure how recall and false reuse change across a validation set. If practical AI engineering helps, subscribe and watch the AI engineering videos.